In one of my previous videos, I shared a robot vision positioning method. Following the principle of actions speak louder than words, I did some insignificant work in open source D. First, based on the rules document of the RoboCon basketball robot competition, I set up a ROS simulation environment corresponding to the RoboCon 25 sim package. Then, I developed a preliminary framework for vision positioning based on the field lines corresponding to the RoboCon localization package. I will briefly introduce the work of these two parts below. First, there is a simulation environment. The map was captured from the rules document. In the center of the field, there is a robot modeled with a panoramic camera on its head. The images it captures have a fishy distortion effect. The image data is published in a specific topic. Subscribing to this topic allows you to obtain image data. Now, let me explain the working principle. Firstly, through color space conversion, we extract the white field lines from the panoramic image collected. Then, we perform downsampling through ray scanning to obtain these field line points. Next, we use distance calibration to fit the curve of the relationship between physical distance and pixel distance. By executing this command to start the calibration environment, you will come to a scene where a red ball is placed in front of the robot. In the panoramic image, you measure the distance of the ball to the center of the screen, which is the pixel distance from the ball to the robot. The physical distance from the ball to the robot is set in the launch file that was just executed. The pixel distance from the ball to the robot will be displayed in the terminal after executing the launch file. By increasing the physical distance of the ball by 1 meter each time, and reading the pixel distance, you will eventually obtain a table. Fill this table into the config folder of the RoboCon localization package in the dist table txt file. The left side of the colon is the physical distance in meters, and the right side is the pixel distance in pixels. When you run the program in distance lookup, it will fit the distance relationship curve and correct the distortion in the panoramic image. The corrected field line sampling points will then resemble the shape of the white lines on the field. Using the ICP method, we match the corrected field line sampling points to the field line template to deduce the position and orientation of the robot on the field. The origin point in this figure is at the center of the map. The positive x-axis points right, and the positive y-axis points down. The specific positioning values are displayed above the map. This project has been open sourced on GitHub. Updates will continue in the future. The steps to run the program are written on the project homepage. You can find the project address in the top comments of this video. Running this project is straightforward. First, download the source code and compile it following the steps. Then, execute ROS RoboCon localization. Launch in the terminal window. Press Enter. This will start the entire positioning system. Adjust the display window and find a way to move the robot. using our QT robot steering to control its movement. Let's begin. This way, you can experience the positioning effect in the simulation environment. Since only image data is used here without wheel odometry, students with field conditions can try holding a camera and conduct field tests on the actual field. If you don't have a panoramic camera, those USB fishy cameras available on Taobao for a couple of $100 are also worth trying out. Currently, this positioning method is still a preliminary framework with plenty of room for optimization. For instance, white feature points outside the field sometimes interfere with the line matching, leading to positioning errors. These points can be eliminated by using the boundaries of the red and blue areas. Additionally, these red and blue areas can further enhance the accuracy and stability of the positioning. All these improvements will be gradually implemented in future updates. Finally, dynamic obstacle avoidance and navigation will be added to complete the project. We achieved visual positioning based on the white lines inside the field. Back then, we mentioned those to read in blue areas on the edge of the field. They can assist in the positioning function. What specific roles can they play? Here we've implemented the simple applications. One is to eliminate external interference. The second is to reposition the robot. Let's start with the first one, eliminating external interference. It mentioned that using only the white lines for positioning can be easily disturbed. Sometimes, white information from outside the field can interfere with the line matching, causing positioning errors for the robot. So, we can use these two red and blue areas to eliminate this external interference. Let's see how it's done. In this panoramic image, the purple cross marks represent the sampling points of the field's white lines. The light blue cross marks are for the sampling points of the inner edge line in the blue area, while the yellow cross marks are for the sampling points of the inner edge line in the red area. According to the rules, these two red and blue areas are the operation areas for human team members, so there is likely to be various obstructions. The information might be incomplete. However, these two inner edge lines should not be crossed during the match, so there should be no obstructions, and the information will be relatively complete. After correcting the distortion of the red and blue area's edges, we get these two arrays. You can see that their shape restoration is quite high. Let's have the robot rotate around the field boundary to observe the restoration effect of the robot at different positions on the field relative to these red and blue lines. You can see that as the robot patrols along the field edge, the restoration effect of the red and blue lines is quite ideal. However, the closer it gets to the edge of the field, the more external interference points come into view. Alright, can we sample only the white field lines within these red and blue lines? This way, the external information won't interfere with the line matching. Hey, and the effect is like this. You can see that all the interference points outside the red and blue lines have been eliminated. Let's have the robot patrol around the field edge for a full circle to observe the effect of eliminating external interference points at different positions on the field. You can see that by using the red and blue lines, all external interference is completely eliminated. Great. Let's try the positioning effect in this scenario. We will continue testing using these two commands. After starting, you'll see several windows like this. One is the simulation environment. The second is the effect of line matching. And the third is the robot's positioning effect. The icon in the middle represents the robot's position, the black short line indicates the robot's orientation, and the bottom panel is for controlling the robot's speed. Great! Let's set the forward speed to maximum. Control the robot's heading through the rotation speed, and then start skirting the edge, daringly exploring dangerous areas to see if there's any interference from external information. After eliminating the external interference points, you can see that the line matching effect becomes very stable. Even when close to the edge or slightly out of bounds, the positioning effect remains stable. This is the first role of the red and blue lines, eliminating external interference. Let's take another look at these red and blue lines. Have you ever thought, since white lines can be used for positioning, why not use these two sets of red and blue lines? Moreover, they also carry color information, essentially providing directional information. So, they not only offer positional information, but also directional information, making them a more perfect reference for positioning than white lines. Based on this feature, a simple implementation of a robot's repositioning function was carried out, combining it with INU attitude sensing. First, let's have our robot launch an attack. Hey, maneuver around and break through to the basket. At this point, the opponent adopts a fouling tactic and knocks our robot down directly. It flips over, then turns half a circle and rolls a few times. You can see that at this point, the robot's positioning has gone awry, and the line matching has been a lonely affair. Then the opponent's robot fails to avoid obstacles and directly crashes into our robot, sending it flying. It flies over here. Great. Suddenly, the robot gets a surge of energy and stands up tenaciously. Look closely. Now the line sampling points are all skewed in the terminal, and the positioning is incorrect. See that? The terminal indicates that the robot has been repositioned based on the red and blue lines. The coordinates and orientation are as follows. Exactly where the robot stood up in the simulation environment. This is the repositioning effect achieved by leveraging the red and blue lines. Now control the robot's movement. Hey, the robot can once again continuously position itself correctly. Launch another attack. Here we go again. Flip over, turn around, roll a bit, and get knocked out again. But it stands up once more. See that? With this level of positioning stability, even with such a lively chassis structure. And this one. Oops, I mean this one. The robot can freely move around the field, touching, climbing, rolling, hitting, no matter how intense the battle gets. As long as it can stand back up on its own in the end, it can instantly restore its position on the map without any worries about positioning. This allows it to freely unleash its youth on the playing field. Along with various components.
You are nothing!
Great. All the Funkin tool lines mentioned in the video are open source on GitHub. The link is provided in the top comment of the video. If you find this project impressive, please give it a thumbs up or support. Your encouragement is my biggest motivation for updates. If you have any better ideas or thoughts, feel free to leave a comment in the section below. Let's learn from each other. That's it for this video. See you next time.